this is some ongoing work that I'm doing with Dr. Shogwell. And sort of the starting point you're starting to look at is sort of the family of data structures that support stack, queue, and deck operations. So what we're paying special attention to here, in addition to asymptotics, is sort of practical issues and in particular constant factors. And one of the motivations that brought us to this line of work is to bring some of the results that we had previously in a couple previous papers, which were in sort of the C++ setting and sort of the high performance setting, over from there to functional languages. And part of the challenge is in exactly that kind of porting of results. So in addition to these stacks, queues, and decks, we're also interested in sequence representations that support splitting at a specified position and concatenation in logarithmic time. The interest there is in dealing with kind of parallel algorithms in functional languages, and also some string application useful there too. Okay, so sort of to start off with our motivation, let's look at linked lists. So this is a widely used data structure. It has sort of a special place in functional languages, probably because it's familiar, simple, and easy to implement. But when you're thinking about storing large sequences, it has some major limitations. Wastes a lot of space. Because of all the indirections, it's bad for traversal. And there's this excellent ICFP keynote by Guy Steele from ICFP 09, where he kind of lays out the case for why you wouldn't want to use linked lists in a parallel setting. Now, there's been a great deal of work on linked lists, nevertheless, kind of going back to Kutter coding at least, where the idea is to sort of deal with the many indirections by kind of coalescing items into kind of chunks. This is kind of a dynamic process. There's been follow-up work in the context of ML back in the 90s by Xiao et al. And putting some of this kind of smarts into compilers. So it gives you a more compact representation, faster traversal, but it still has the problem that it's more complex to implement than than just linked lists. So you have this complexity, and it's still bad for parallelism, and it doesn't really automatically give you kind of ephemeral access, which kind of turns out to be useful for doing really fast, efficient access on the ends of the sequence. So there's been in following years, there's been some work on a variety of structures, one of which is this kind of dynamic array structure. It gives you a pretty compact representation, and it's fairly flat, so you can access any item in most in two directions. But it seems to support kind of stack operations and random access all the way. Now there's in the imperative world, there's a vector data structure which is pretty popular, and it's part of the standard template library in C++. It's been attractive because it has fairly fast access to the end of the sequence, and because it's just a big array internally, it gives you fast random access. But the problem is that every time you want to resize, you actually end up copying all of the items. And that, even though you have good asymptotics, that turns out to be quite inefficient because of all the overheads from cache misses and such things, memory-related things. And it may be not so well appreciated, but actually the space efficiency of this structure is worse in the worst case than linked lists. That's because you can waste up to, if you have word-sized items, and you're spending 4 words per item in the worst case. Okay, so switching gears a little bit, there's been a rich history of work in functional data structures, and one of which is particularly interesting for us is the finger tree. This structure has support for DEC operations in constant time, and also splitting and concatenation in logarithmic time, so it has the asymptotics that we like. But as you can kind of see from this picture, it has lots of indirections, and that actually leads to 4 constant factors if you just implement it in the textbook way. Okay, so we kind of had a quick tour of the landscape, maybe a sample, but let's sort of stop and say what it is we're trying to do here. So we're particularly interested in structures that have a compact representation. We're aware of results in some of our work and other work where you can get quite compact representations in the ephemeral setting. You can also get quite efficient access, say, on the ends of the sequence in the ephemeral setting. So time efficiencies can be quite important in certain circumstances for certain algorithms. So that's something that we'd like to have. And of course, we'd like to support a variety of sequence representations and generalize that to something with sort of the profile of a finger tree. The reason for that in particular is having this kind of flexibility to sort of piece apart a sequence for parallel execution, be able to kind of resize those individual pieces in parallel and then join them back up at the end to form a large logical sequence. So this kind of thing is quite useful in parallel programming. And we want it to fit nicely into a functional language. So we like to kind of resolve the sort of tension that we see between sort of the efficiency levels you can get in the ephemeral setting and the fact that you also want sort of the convenience of programming a persistent structure. So the starting point for this work is chunks, and what I mean by chunk in particular is just a small array of a fixed capacity where we store items. The advantage being that when you write an item, you just write it once and you don't have to copy like you do with the vectors. It's friendlier for perhaps for GC, but definitely for traversal because you have this kind of more contiguous layout. It's kind of in a middle ground. So, in Camel or Camel implementation, we just represent a chunk like this. We have an array and the size field, which is allowing us to have a fixed capacity, but a configurable number of items to store in the sequence. Okay, so it may seem kind of simple to go from there to larger structures, but in fact there's some fairly subtle pitfalls that pop up that we found, and this is from some prior work that we did on the imperative chunk sequences. So when we looked at this more carefully, there's a fairly popular chunk sequence in the standard template library called the DEC, the double-ended Q data structure, and this internally is represented as a chunk sequence. What we found is that the structure wasn't properly or carefully amortizing all of the expensive operations, which is allocating and deallocating chunks. What you could do is if you craft the right push-pop sequence, you could make it 10 times slower than it is on average. And actually there's sort of a spectrum of bad sequences, so it's not just this worst-case sequence, it sort of pervades similar sequences. And the solution, though, is just really simple. All you need to do is have, for example, one way of doing it that we worked out is on the end that you care about, on the end of the sequence you care about, if it's just the front, then you do just the front, but if it's both ends, you allocate a couple two chunks, and that gives you sort of the hysteresis you need to amortize the chunk, the allocations and deallocations for any push-pop sequence. Okay, so that was sort of one issue that came up. Another issue that's, seems like a minor issue, but actually can be quite problematic is the fact that, if you're in this regime of using fixed capacity chunks, you don't want to allocate a whole chunk for a very small sequence, because if you have sequences of sequences, then you end up spending quite a lot of memory. And sort of anecdotally, I can say that I know of I've heard of cases where industrial, industrial settings, they've had to re-implement large portions or an entire STL just because of this issue, where they thought they had to do it. So really, the experiment, or the solution, sort of the obvious solution that we're experimenting with here, is just to have a special representation for small sequences. So anything with 4 or fewer elements, we have a special constructor for that. We have one for kind of anything between 5 and 18 items, and then or the large general purpose structure for long sequences. Okay, and we call that the adaptive container. Okay, so in the paper we had one very basic experiment just to kind of look at what happens when you use this chunking technique in OCaml. So we just have a program that pushes a bunch of items into a structure and then pops them. So here I'm showing the results, and basically, well, the lower is better because we have execution time on the y-axis. We're doing multiple, we're kind of taking the sum of multiple runs. We do small sequence sizes, and then one run for the largest sequence size, so we get the times to kind of plot nicely. So the first kind of result here, the singly linked list performs quite well when you have small sequence sizes, and it degrades horribly when you have large ones, as you would expect. The fixed capacity array is best because if you know the size in advance, it's much more efficient to do that than just allocate it. The vector of items, which is just a vector of individual items, the kind of STL style vector, that's not so great. It's kind of this blue curve there, and it's aside from the linked list, it's the worst. The vector of chunks, the chunk vector, does considerably better, especially for larger sizes. And the adaptive version of that chunk vector, which is like we call it adaptive there, that one, well, you wouldn't. So the good news is that it's not much worse ever than the chunked vector. And what that's telling us, well, all you get from the adaptive version is a more compact representation for small sequences, but you have this additional complexity for pushing and popping, and it just turns out in this particular case, we're not paying a huge cost for it. So that's a good sign at least. Okay, so right. In past work. In past work, what we were motivated to develop a kind of a finger tree-like structure, which we were going to use, which we ended up using to develop some high-performance graph traversal algorithms, parallel graph traversal algorithms, in fact. And where we started in this work is where we started implementing kind of an imperative, an ephemeral version of the finger tree. And instantiating that with chunks. So we would store the vertices in the frontier in the chunks, and we would push and pop chunks from the finger tree. So we sort of treat the finger tree as a black box. Now, right. So this sort of technique has been around for ages. It's typically been called ropes. What we found is that there's an additional subtlety here. With respect to, in this case, to managing the chunks, and it has to do with when you're concatenating. So if you're not careful in how you deal with the concatenation, you can end up with very sparse sequences, or sequences of very sparse chunks. So you'll be wasting lots of space. We have a fairly simple technique where basically when you're concatenating, you have to be careful to sort of preserve the invariant that any two consecutive chunks, the size of the number of items in those chunks combined adds up to at least the capacity of a single chunk. And if you do that, then you get the property that your sequence is going to have all the cells in the chunks you're going to have at least half full kind of chunks overall. You can actually do better and get more kind of denser representations where your chunks are closer to full on average, if you're willing to do a little extra work when you're concatenating, but it doesn't affect pushes, pops, or splits, in fact. Okay, so what I think is really cool about this actually is that we started off assuming a finger tree as sort of being the supporting data structure in the middle, but it turned out that when we looked closer, all we had to do actually was take sort of this hysteresis, where we have kind of buffers on the ends. In this case, we have a deck, so we have two buffers for each end to kind of help us amortize the cost of pushing and popping and creating chunks. So we have that trick, and then we have basically the way of dealing with the sparsity issue by making sure that we don't allow sparse chunks. If we have these two tricks and we combine that with a fairly simple bootstrapping, like kind of recursive bootstrapping technique, we get basically a brand new data structure, which has the same asymptotic profile as the finger tree, but with a configurable branching factor. So this is sort of an ephemeral structure currently. What it kind of gives you, though, is sort of the advantage there, of course, is you get a shallower tree representation because of the chunking and the ability to pick the branching factor. It gives you kind of, we actually were able to prove a kind of an amortization property for push-pop sequences, so you get sort of fast access, and I guess sort of, the way to sum it up is it's sort of like, very roughly speaking, it's sort of like the chunk sequence is to the finger tree what the B tree is to the red-black tree. So I think that was a pretty cool side result. And we're partly here working on bringing that kind of structure to the functional world. Another issue in bringing this structure into the functional world is dealing with persistence. Now, I mean, if you bring this if you use a kind of naive, technique, what you would end up doing is every push and pop, you would just do a copy on write. That would be safe, but it would be really slow, so that's a non-starter. Our first attempt, which we have in the paper, well, I'm not going to talk about that because we think it's broken. But since then, we've learned about a really cool kind of way of structuring the data structure. And so just sort of a way of getting around this whole problem. It's called transience, and it was actually mention of that in the RB vector talk earlier in ICFP. The idea is basically that you have sort of two different views of the memory, one being persistent and the other being a transient view. The transient view gives you sort of the special ability to update in place at the expense of having to be careful and make sure that you don't violate the safety. Now, and the way it works, of course, is that you have sort of a way of casting or converting between these two views, and it has a small cost, but it's a small cost and time cost. So I think that's an interesting way forward. We're also looking into ways of sort of getting the benefits of very fast random access, kind of like you have with the dynamic array structure. We have two levels of indirection, but additionally have sort of the same kind of functionality of the finger tree, the chunked finger tree kind of thing. And that would just be, you would do that by, for example, allocating a big table with pointers into the chunks, but then you have to worry about how you deal with splitting and concatenation. Okay, so I mean, this is very much ongoing work. If you're interested in looking at the code or anything like that, we can certainly provide it. Some of the things that we're looking at in the near term is comparing in a few of ML implementations, so Camel and Milton, for example, and we're looking at these interesting new data structures which are quite closely related. There's the RRB vectors, which was already presented in a couple times in ICFP. There's 2 papers on that. There's a fairly new structure called the RAS tree, which is kind of a probabilistic tree structure, but it has essentially, both of those have the same kind of asymptotic profile as the finger tree and also the kind of chunk sequence which I mentioned. Right, and basically, yeah, what we're interested to see is how far we can kind of push in terms of performance and still kind of preserve the nice, clean interface you can get with functional data structures. So that's all.
Can you repeat the questions that you did?
Sure.
So do we have some questions? So I have a question. I happen to know that you are a lucky man. You have a lot of experience implementing sophisticated data structures in C++. So how does the ML hacking compare to that for this problem domain?
Okay, so generally, yeah, how does hacking in ML compare to writing these?
I'm not asking about the performance because
right.
that would be depressing, but the programming experience.
Okay, yeah. So how does the programming experience compare between writing these things in C++, say, versus writing them in ML? Well, it's not. Yeah, I guess my experience isn't maybe so informative in the sense that the applications that we cared about were these kind of high-performance graph algorithms, and those are fairly confined in what they're doing. We haven't been working so much with like a variety of algorithms. Although I'm starting to look at more using this kind of chunk sequence structure in C++ for kind of general, sort of as a maybe as kind of a logical extension to like the STL or something like that. And I think that's kind of interesting, but I can't really say I have much experience kind of on how much easier it would be, except for the usual pitfalls. I think.
Yeah. So I was kind of wondering about a parallel setting for some of these data structures. Is the focus having high throughput modifications to the data structure like push pop, or is it primarily very, very fast traversals? Because you mentioned that you're looking at okay. I worry about synchronization concerns with the chunk sequences.
Okay, so the question is, are we focusing more on high throughput for push and pop, or on traversal?
Like being able to read the data as fast as possible by minimizing.
Well, I think we're trying to do both really well. I mean, there's sort of, I think we have a nice baseline in that we have these really fast C++ implementations, and we can compare directly with those. And I don't think there's really a kind of a fundamental, I don't see there being a fundamental tension between the two. And then you were asking about concurrency aspects, or is there? So one of the cool things about this structure is that you can kind of physically break it into independent pieces, so that you can operate on them. And what it gives you is the ability to resize those pieces independently without any synchronization, and then join them back up efficiently using the concatenation. So actually, there's no synchronization at all in this structure. The only synchronization you might have is if you're going through an allocator where you have to synchronize, but otherwise it's not.
Oh, so it's not a mutable.
It is a mutable data structure, but maybe what's a little weird about this, like with the transient interface, what you have is the ability to kind of take the persistent data structure and kind of bring that into an ephemeral setting. So you could imagine the way it would work is you'd sort of have a parallel processing where you're working on, at the high level, you're working on the persistent structure, and when you switch to like a kind of a smaller problem size, you go into a transient kind of mode, and that's where you're using kind of the fast kind of ephemeral access to your advantage to get really fast kind of sequential kind of base cases. But then you switch back out into the persistent mode when you're done and kind of join things up. So you have kind of the best of both worlds. You have to, of course, be careful. If you're not careful, you could easily, if you don't use the transient mode properly, you could easily create race conditions and stuff. So one way to deal with that would be to have linear types or something. I think that would be a really cool thing to have for programming with these kind of transient structures. I actually don't know if anybody's looked into that in sort of that setting, because transients come from closure, and I don't know if anybody's looked at kind of the typing aspects of it.
The rest people in the room are nodding. So if we don't have any more questions, let's thank our speaker and take a break.